Welcome to the hyperbolic compression chamber, where my brain is being compressed by the work of the people at LeetCode.com, and they must be stopped. That is why I formed the hyperbolic coding chamber, to eradicate all the problems on the platform. And we are making good progress on that. But we don't have a lot of time today, and a slightly shorter session today, but not overall time. I just spent about an hour doing some more reading and some more thinking. And this problem is very interesting, but I think we have good things to do. But we have a comment from Sorry with actually a pretty cool profile picture, I have to be honest, as I've never seen anyone do this before. Keep up the suffering. You too, my fellow human companion. So, yeah, thanks for the comment. Yeah, it feels strong, man. Feels strong. But this problem has been controlling my brain. Ones and zeros. I think we're getting closer. I feel like a mad scientist. Okay, in my other room, I have all these papers on the walls. I have dots and strings tying this algorithm to this algorithm, and here, and specific algorithms to here. So I think we've almost solved the mystery, right? And I think it could be possible. We won't solve it today, but I have a sticky sensation about tomorrow. So I believe, and also a lot of growth from this problem, which is also the beauty in medium problems, but this problem has awoken something in me, and I think I'm on to something. There probably are going to be some changes to the schedule, so feel strong, man. Also, I was able to wake up early. I think I figured out the cheat code. The way to wake up early, okay, the way to wake up early is to go to sleep earlier. And I feel like that might have been obvious to other people, but I really thought I could solve my way out of it, because I just hate going to bed when I don't want to. But I think that's the actual problem. So even if we don't solve this problem, we've solved another problem for everyone else on the planet. If you want to wake up earlier, we just have to go to bed earlier. So that's the wave. That being said, I don't want to talk too much because I don't want to take away from the solving time. So for the timer today, we have 38 minutes. And I'm going to jump into it. So we were trying some nonsense thing here, basically, where I was going to try a different version. No, this is not the nonsense. Let me see. No, this is just Dijkstra's. Here we had a nonsense version. We were trying to do something special here. That is not the wave. This is the wave. I believe in Dijkstra's shortest path for this, except we can change it to do longest path. And I think that is actually the wave. I've had a sneaky suspicion about dynamic programming problems being able to be reduced to path problems, and I've solved maybe 4 or 5 of them with a very unoptimized graph implementation. Now my sneaking suspicion has been corroborated, and I now know, after reading some more supplementary reading, that a lot of dynamic programming problems can be reduced to shortest path on a DAG. And I knew it. I felt it. The intuition was building. I felt it. It's why I always tried to formulate dynamic programming problems as graph problems, because it just works for some reason. And I'm not certain why, but now that we know that it's possible, I was going to abandon Dijkstra's because I thought I was just being a nut. But it actually seems possible. So this is actually the wave, okay? So I'm going to see if we can beat this out. The main issue, there's another thing I didn't understand. I was uncertain if Dijkstra's could work on a cyclic graph, and it can. It just has to be that all the weights are positive. So it's very much possible for us to solve it this way, hopefully. But I thought the strangeness we were seeing here meant something was wrong, but I don't think so. I think what this is basically just telling us is that it just happens to be that the shortest path let me make this output easier to read. Just remove some cognitive load, just adding some more comments. So our parent array, which is showing us the path we're taking through the tree, the shortest path to all these nodes, it's basically starting from start and just going straight to that node, right? Because the graph is pretty much the graph is fully connected, the shortest, since Dijkstra generates the shortest path between all vertices, since the path is since the graph is fully connected, we can literally just go to the vertex we want to. So I think the way to fix this would be to make the graph acyclic, or pretty much make the graph, well, the graph is cyclic right now. And undirected. I think the wave to solve this problem would pretty much be to turn the problem statement into a DAG. And we were sort of creeping up on this with this comment here. What if no more fully connected graph, edges change on vertex viability? So maybe that could be the wave. Right now, the way we consider our neighboring edges is by considering, you know, the graph is fully connected. So we just consider all the elements in the graph, or all the vertexes in the graph. What if we only were able to consider nodes in the graph for which we can actually travel to given our current standing? We had something like that here by using M and N and the corresponding zeros and ones in the string to give each edge a weight. Largest subset with at most 5 zeros and 3 ones. The problem with each vertex edge changing, the edges on each vertex changing with respond to viability, depending on viability of the options, is that the graph is too variable. Presumably we would need a graph. We should just design a graph such that the edges don't change. I think this could work. I feel like I'm changing the graph on each iteration, but in practice, that might be okay. The real test is this one up here. You take 0, 1, 1. This has to have 4 zeros in it, because if you take this route, you can't do anything else. If you take this route, there's no other route you can take such that you would end up with path that is longer than 1, which is not even really a path. Like we said earlier, if we ran Dijkstra's on every single node, take this one, then you would take one of the nodes, the viable, take this one, and there'd be no more viable paths. The shortest distance, I want the shortest distance to S. We could generate the graph. You could just get the potential edges. Potential edges would change for every node. Based on the node's ability to do. I think I see what we have to do. I think that's why I said we might not solve it today. I think there are two paths that remain now. If we bring this back up top. This is dead. I think it's still possible to solve it the way I was going to solve it before. We just change it to the maximum way to get to. Can we just change it to the maximum way to get to? I forgot to update the day. Can we just change it to the maximum way to get to? Options, or you can represent it as DAG, or wait for edges to represent number. Yeah, that one's dead. Or we could represent it as a DAG. But I feel like we could also just, maybe that's a misunderstanding of how Dijkstra's works. Each vertex neighboring edge is changed depending on viable options. Or we can represent it as a DAG. What if we don't represent it? Couldn't we just use Dijkstra's as it is now, except change shortest path to longest path? The problem is that doesn't take away the rule part of M and N. It ends up being very nutty. if we update the distance? I think we just need to choose one and run with it for the time being. Representing it as a DAG sounds difficult. For each vertex, neighboring edges change depending on viable options. This is essentially the same as representing it as a DAG. What if we keep the graph for the connector and just send it to max? Three paths here. For each vertex, neighboring edges change depending on viable options. Or if we did it with this one, shortest path, if it's all -1, it would just be one. I see. Change depending on viable options. The way they change is twofold. The set of edges is equal to Texas. Set of edges equal to Texas, where it's possible to move. The edge we choose is the one of least cost. I see, and I think with those two things together, it ends up making more sense. Also, for calculate weight, there's no actual thing, there's nothing special happening here. I think what's interesting that's happening here is we're looking for the shortest path, and there's an interesting correlation. If we add m and n together and get 12 and subtract the length of the string is the actual value of the strings here. We're doing all this special stuff up here. That's all it really comes down to. So you could replace m and m with the string or maybe not. This version does allow us to have infinity as an option, which pretty much means we shouldn't take that route. This way, when we want to get the pool of edges, neighboring edges, we can just calculate the weight for all of them. No, I think I'm getting confused. I think we can keep this function. What I'm trying to do is break the subset, the potential choices, down to edges for which we can still travel to. Problem with the vertexes where it's possible to move things that depend on a current M and N. We don't really have a concept of a current M and N in this Dijkstra's version. Yeah, I think we can make this work. The neighboring edges you can choose from. We can just make them like const edges. And then what we'll have here is we'll have the zeros and ones for a vertex, which is just the one, the string it is in the string. Then we'll have a cur M. We'll have a cur M, which is equal to 0, and a cur M, which is equal to M minus zeros, and a cur N, which would be N minus ones, and the potential nodes that we can travel to will depend the nodes we can actually travel to will depend on the ones that don't break this rule. So say edges is equal to which will give us the index. And then we'll want to filter the indexes based on a little block of code that we'll write here. Cur m, all right, we're gonna wanna get the zeros for the index now. Greater than or equal to 0. Cur n minus edge 1s which would give us our possible edges. Or possible vertexes which just return return 0, and we need to add our case here, which is the one where it actually shows choice. M is equal to 9. N would be equal to 3, and we're looking for is 1 on 1, 0 0 1. Oh, it's greater than or equal to 0. We'll filter and index does not equal v. So we'll filter ourselves out as well. And this actually looks really good, but unfortunately, I have to go. Rip. But I think I might finish this one later off camera because I'm really excited about this one. But yes, we have to go.